Hi, my name is Miguel Macias and I'm a first-year graduate student at Florida State University. This video presentation is an assignment for a materials course that I'm taking this fall, and it's mainly focused in the chemical applications of group theory. Today, I'm going to talk about a silicon analog to benzene, and I'm going to highlight some aspects related to symmetry. So, let me first start with the question. Does a silicon analog to benzene exist? And if does, would it be aromatic? Let's first define aromaticity. Aromaticity is a property that occurs in cyclic planar compounds, and it consists in the delocalization of electrons, resulting in extra stabilization. So the first criterion to be met is planarity. Benzene is known to be planar. It has D6H symmetry. On the other hand, silabenzene it's not planar. It's more like a chair-like structure with the 3D symmetry. In order to find a cyclic planar analog to benzene made of silicon, the symmetry should not be restricted to the D6H group. A subgroup may work as well. We can start by showing what happened to the basic functions when we lower the symmetry of the molecule. Let's look at the D6H character table. And we need to find the irreducible representations that contain the s orbital, the 3p orbitals, and the 5d orbitals. We can see that the s orbital belongs to the A1U irreducible representations, the Bz to the A2U, and the dz square to the A1G. The orbitals px and py, dxz and dyz, dx square, y square, and dxy transform together and represent three sets of double degenerate orbitals. We can do the same inspection with the D2H character table. After finding the irreducible representations that contain the orbitals, we can build a diagram like this one. And we can see what happened to the double degenerate orbitals when we lower the symmetry of the molecule. For example, let's look at the double degenerate px and py orbitals. They belong to the E1U irreducible representation in the D6H symmetry. When we lower the symmetry to the D2H group, we can see that the orbitals split into two independent irreducible representations. Now, the py orbital belongs to the B2U and the px to the B3U. Now, let's go back to the D6H character table. As we just saw, we can eliminate the irreducible representations that contain degenerate orbitals, as they split into two independent representations when we lower the symmetry of the system. We can also get rid of the C6, C3, S3, and S6 symmetry elements, as they don't exist in the D2H symmetry. After rebranding the symmetry elements and the irreducible representations, we just generate a table that is exactly the same that the D2H character table. We just prove that D2H is a subgroup of D6H. To go even further, we can say that D2H and D6H are subgroups of the OH group. To verify this fact, the listener can do the exercise. Now let's take a moment to think of this procedure. We can start with benzene, and we are going to replace the carbons with isoelectronic silicons. It also makes sense to replace the hydrogens with another isoelectronic atom, being lithium a perfect candidate. Knowing that silicon can form 3-centered 2-electron bonds, we can place 4 lithiums between 2 adjacent silicons to form a structure like this. and the two remaining lithiums can be placed above and below the plane of the ring. Here's a side view to clarify this structure. Silicon 6 lithium 6 has this D2H symmetry, and using theoretical calculations using the density functional theory, better known as DFT, it has been proved that this molecule is a global minimum. Also by calculations using the nucleus independent chemical shift, or NICS, and please do not confuse it with NCIS, it has been proved that this molecule is aromatic. NICS is a criterion used to rationalize aromaticity. It is based in the computed values of absolute magnetic shieldings. Negative NICS values denote aromaticity, while positive ones are an indication of anti-aromaticity. For instance, benzene has a value of negative 7.60 and silicon 6 lithium 6 of negative 3.95. To further support the aromatic behavior of this molecule, we can compare the HOMO and LUMO orbitals of this molecule with the ones that belong to benzene. We can see they are pretty similar. In conclusion, we can say that silicon 6 lithium 6 is a cyclic planar compound that is aromatic and it's analog to benzene. Now that we know it exists in silica, the next step is to obtain it in the lab, a task that is meant to be fulfilled by experimental chemists. Thanks for watching.